This unit starts Chapter 2, in particular sections 2.1 and 2.2, which talks about complex numbers and quadratics. Our objective in this lecture is to basically deal with arithmetic using complex numbers and reintroduce complex numbers. You should have covered that in previous math classes, but we'll cover it again. Okay, this is going to be important because we're going to run into imaginary roots of quadratic functions and other polynomials. And after that, we're going to talk about graphing quadratics and finding the minimum and maximum of a quadratic. Okay, so imaginary numbers. Okay, sometimes we will encounter a square root of a negative number. For example, the square root of -4. Okay, this is especially going to be the case as we use the quadratic formula that minus b plus or minus b squared, square root of b squared minus 4ac over 2a. Okay, that whole thing under the square root will occasionally end up being negative. And so we need to have a way of dealing with that. And so mathematicians introduce this concept of the letter I to represent the square root of -1. Okay, so I can now express the square root of -4 as the square root of the positive number 4, okay, times the square root of -1, or basically just 2i in this case. Okay, and the reverse, okay, if I is equal to the square root of -1, I squared will equal -1. Okay, so the set of complex numbers, okay, the standard form for this is going to be a plus bi, where a is the real part and b is the imaginary part. It's really bi is the imaginary part. Okay, both a and b are going to be just real numbers, so they don't have to be integers. They can be real numbers like square root of 2 or pi over 4 or -3. Okay, they just any real number is fine. Okay, and we can do arithmetic with complex numbers. Okay, we can add, subtract, and multiply complex numbers. And when we do that, we basically treat I like any variable that we encounter. Okay, like x or y. Okay, so when I have 5 minus 2i plus 3 plus 3i, okay, I group the variable or the I letters together and I group everything else together. Okay, so in this case, the 5 plus 3 will get grouped together and the minus 2i plus 3i get grouped together. And when I complete these things, it becomes 8 plus 1i, or if you prefer, just 8 plus i. Okay, subtraction works the same way, and when it comes to multiplication, we FOIL everything out. Okay, so if I FOIL this thing out, I end up with 15 plus 15i minus 6i minus 6i squared. And the I squared is going to be important because instead of I squared, remember we said if I is equal to the square root of -1, I squared will equal -1. So making the substitutions and grouping the 15i and 6i together, I end up with 15 plus 9i minus 6 times -1. Okay, or because the -6 times -1 becomes +6, this whole thing really becomes 21 plus 9i. Okay, before I do division of complex numbers, I need to introduce the concept of the complex conjugate. Okay, we ran into something earlier when we did square roots, okay, and square roots in the denominator. Okay, but the complex conjugate of a plus bi is going to be a minus bi, because when we multiply these two together, we end up with a real number. The imaginary part basically disappears. And we did this when we had square roots. Okay, so a plus bi times a minus bi, okay, when we FOIL it out, simply becomes a squared minus b squared I squared, or after making the substitution for I squared, it becomes a squared plus b squared. Okay, we saw something similar when we had square roots in the denominator. Okay, you know, if we call that kind of like the square root conjugate, okay, instead of multiplying by, in this case, if I had 2x divided by 1 plus the square root of 5, okay, I would multiply by the conjugate of that, or the 1 minus the square root of 5. Because when I do that, the square roots basically disappear. And remember, I is nothing more than a square root of -1. So it is very similar to this concept of square roots. Okay, so this is what happens in 2x divided by 1 plus the square root of 5. Okay, we multiply top and bottom by the conjugate. and I end up with something that looks minus x times the quantity 1 minus the square root of 5, all divided by 2. I do the same thing for complex numbers. In this case, 5 minus 2i divided by 3 plus 3i. Okay, and okay, and so when I do this, okay, notice that the bottom becomes, so I multiply top and bottom by 3 minus 3i. Okay, and so the bottom becomes simply 9 minus 9i squared, or after I make the substitution for I squared, 18. And after I simplify, it simply becomes 7 plus 3i divided by 6. Okay. Unfortunately, I think I have an error in the top part because I assumed I had the same multiplication as before, but that was 5 minus 2i times 3 plus 3i. Okay. In reality, it should be something different, so let's do that one on top. Okay. It's going to be equal to 15 minus 15i minus 6i, and then minus 6i squared, which becomes 15 minus 21i plus 6, and that's going to equal 21 plus 21i. Okay, not 21 plus 9i, but I still can take out a 3, so this one then would become 7 plus 7i. Okay, so sorry about that. Okay, so moving on. Okay, we're going to also deal with the principal square root of a negative number. Okay, so if b is a positive real number, the square root of minus b is going to equal I times the square root of b. Okay, and so we're not going to deal with the plus minus aspect. Okay, it's simply going to be this positive root. Okay, so for practice, let's look at the square root of minus 27 plus the square root of minus 48. Okay, again, we would pretty much do the same thing. Minus 27 is going to be I times 27 plus I times 48. Okay, but 27 is actually the square root of 9 times 3, and 48 is going to be 16 times 3, or basically 3i root 3 plus 4i root 3, and again, adding them all together, I end up with 7i root 3. Okay. In the case of the square down below, okay, we can FOIL it out, or if you remember it, it becomes minus 2 quantity squared plus 2 times minus 2 times square root of 3 times I minus and then plus square root of 3i quantity squared, which then becomes 4, the 2 cancels, plus 4 root 3i, plus square root of 3 squared is 3, I squared is minus 1, so that becomes that. 4 and the minus 3 become 1, plus 4 root 3 times I. Okay, so that's how we're going to be using i's and square roots here. Okay, so like I said, we're going to encounter this in the quadratic equation. Okay, minus b plus or minus the b squared minus 4ac over 2a. Okay, this equation has two parts. The first part being that minus b over 2a. And this is important because it gives us our axis of symmetry. This is where the x value, where the left side and the right side will be mirror images of each other. The part square root of b squared minus 4ac, that's actually called the discriminant. And if the discriminant equals 0, there will be exactly one real root to this to the quadratic. If the discriminant is going to be greater than 0, there will be 2 real roots, and if the discriminant is less than 0, I have no real roots, okay, but 2 imaginary roots. Okay, So, in practice, let's look at this, okay? Find the roots of x squared minus 2x plus 2. Okay. This is not going to factor, so I'm going to just stick it right into the quadratic equation. Minus 2 plus or minus the square root of minus 2 squared minus 4 times 1 times 2, that's the 4ac, all over 2 times 1. Okay, simplifying this becomes 2 plus or minus the square root of 4 minus 4 times 2 is 8, all over 2, or basically 1 plus or minus square root of minus 4 becomes 2i over 2, or basically 1 plus or minus I. Okay, so this is my discriminant right here, okay, the square root of 4 minus 8, or minus 4. It's less than 0, so I'm going to have two imaginary roots. In this case, 1 plus I and 1 minus I. Okay, that 1 is going to be my axis of symmetry, which means if I graph this on an xy plane, x equals 1 will be my symmetry line. Okay, so let's talk about the forms of a quadratic. Okay, we're pretty much familiar with the ax squared plus bx plus c. That's the general form of a quadratic. Okay, the standard form is going to be where f of x is equal to a times the quantity x minus h squared plus k. Okay, this is also sometimes called the vertex form because the value h comma k is going to be my vertex, where the vertex is, again, that minimum or maximum point, or the point where the parabola turns around. Okay, and so the vertex is going to be given by that h comma k. And this whole a times x minus h quantity squared plus k, this is nothing more than us putting the x squared, the parent function, through a series of transformations. Okay, and that's going to help us in drawing the parabola. Okay, because the value of a in a times x minus h squared plus k is going to be helpful in drawing the parabola. If a is greater than 0, my parabola opens upwards. Okay, so it'll look like this. Okay, and if a is less than 0, the parabola is going to open downwards. Okay, it'll look like this. Okay, and the line x equals h is the axis of symmetry. So in this case, my h would be equal to minus 2, okay, and so that's my axis of symmetry. In the form ax squared plus bx plus c, that same line is minus b over 2a, so this is going to be my h value. Okay, in drawing the parabola, I would also try to find any x-intercepts by solving ax minus h squared plus k, or by effectively solving ax squared plus bx plus c. Okay, I can also find any y-intercepts by calculating f of 0. Okay, and that gives me various points that allows me to connect up using a parabola. Okay, but thinking of it as a set of transformations, okay, transformations of the parent graph f of x equals x squared, okay, the x minus h part basically says I'm going to shift my parabola, okay, my x squared parabola, h to the right. Okay, if a happens to be negative, okay, then I'll be flipping it upside down, okay, or reflecting it over the x-axis. And meanwhile, I'm going to be shrinking or stretching the y-axis by that constant a. And the plus k basically says I'm going to take this whole parabola and shift it k units upwards. Okay, so this is nothing more than taking my x squared and sending it through a series of transformations. Okay, so graphing from the general form. Okay, again, I know my axis of symmetry because it's simply that minus b over 2a. So the x-coordinate of the vertex is minus b over 2a. The y-coordinate, I'm basically going to take that x value and stick it into f of x to find what the y value happens to be. Okay, so for practice, graph this quadratic equation minus x squared plus 4x plus 1. Don't use a calculator, okay? Everybody can do it on a calculator, yes. Okay, but then let's look at it and ask ourselves, what's the vertex in this case? Okay, well, our vertex is minus b over 2a, or basically 4 minus 4, that's the minus b, over 2a, 2 times minus 1, okay, or basically 2. So at x equals 2, okay, that's going to be my axis of symmetry. Does it open upwards or downwards? Well, a is minus 1, so it's negative, so it's going to open downwards, okay? It's going to be something that looks like that. What are the roots of this equation? Okay, well, the roots of this equation, I'm going to have to do that. It's going to be minus b, which is minus 4, plus or minus the square root of b squared, which is in this case 16, minus 4ac, or minus 4, all over 2a, which is 2 times minus 1, or minus 2. So again, this is going to give me x equals 2, plus or minus 16 minus 4 is the square root of 12, okay, over 2, square root of 4, okay, so it becomes 2 plus or minus the square root of 3. Okay, so those are my real roots. Actually, it's plus 4, sorry, meaning then that this becomes square root of 20, or 4 times 5, and 2 plus or minus the square root of 5. Okay, and so I would have something that looks like this as a parabola. Okay, sticking in f of 2, okay, because that's my x value, but my y value would have to be minus 2, f of that, which would be minus 4 plus 8 plus 1, or basically 5. So this vertex here is going to be 2, 5. Okay, and the y-intercept would be when that equals 0, so y-intercept will be 0, 1. Basically, f of 0 is going to give me 0, 1, and so that would be this point. Okay, so that's how we could graph our parabola. Okay, and the vertex is going to be very important for us because the vertex is going to tell me whether my value, whether that vertex is going to be a local minimum or a local maximum. Remember, we did that on our calculator, okay? We told the calculator to find minimum or maximum. Now we're going to be able to do that for a parabola algebraically. Okay, because if a is greater than 0, okay, remember, my parabola opens upwards and my vertex will be a minimum. Okay, so if it opens upwards, it's that, and this vertex is going to be a minimum. On the other hand, if a is less than 0, my parabola will open downwards, and now my vertex will be a maximum. Okay, the domain of my quadratic function is basically minus infinity to infinity. The range, however, will be if it's a minimum, okay, if a is greater than 0, it means I have a minimum, and so I'm going to be going from that minimum, okay, that x value, the y value of that vertex, okay, to infinity, so basically from here on up, and if a is less than 0, then it opens downwards, okay, so I'm going to go from this value to minus infinity, or basically minus infinity to that value, f of the vertex x. Okay? And that's going to bring us to how we solve word problems associated with maximizing or minimizing area. Okay? First off, okay, you have to decide what is going to be maximized or minimized. The question should tell you something along that area, okay? In this case, if this is the problem we have about a fence, okay, find the dimensions of the rectangle that maximize the enclosed area. What is the maximum area? I'm not maximizing perimeter, I'm maximizing area. Okay, so that's the first thing, okay, identifying what needs to be maximized or minimized. The second is to basically write two equations in this case, okay? Express this quantity as a function in one variable. So what are we maximizing? We're maximizing the area of the rectangle. Area is equal to x times y. The other equation we have is 120 feet of fencing. So if the perimeter of my rectangle is 120, so that means 2x plus 2y equals 120, or solving for y alone, y becomes 60 minus x. Okay, So once I have that that value for y, I can substitute that into my area equation. Okay, so I'm solving the other one because I'm not maximizing that equation. I'm not maximizing perimeter. I'm maximizing area. So I solve the other one first. Okay, for one of the variables, in this case, y. Okay, when I substitute that in and work it all out, I find out I get a new equation with only x in it. Okay, and in this case, minus x squared plus 60x. Okay, so when I write that function in the form ax squared plus bx plus c and calculate the vertex, I find my vertex is going to be at x equals 30. Okay, if I do that, y equals 30 as well, and the area is basically going to be 30 times 30, or 900 square feet. Okay, so that's how being able to use the vertex to minimize or maximize values is going to be very helpful. Okay, thank you very much.